This is section 7.3, and we're going to work with trig equations. So equations that involve trig functions that are satisfied by only by some values of the variable, and that gives us our solutions. So let's look at some examples. Solve this equation. 2 sine theta plus 3 equals 2. Remember, we're solving for theta. We want the angle theta that makes this true. So, and you're given that theta falls between 0 and 2 pi. This is important to note. That's our parameters. We only go one time around the unit circle, and our answer should be in radians. So even if you come up with a degree for an answer, you need to convert it to radians. So here we go. We're going to subtract 3. We get -1. Then we'll divide by 2. And so we have sine theta is equal to -1/2. So your thought process should be, where is sine negative? And remember, sine is positive in the first quadrant and the second quadrant. And so it's negative in the third and the fourth. The original parameters given in radians. So we remember that. So the angle that has a reference of 30, because 30 has a sine of 1/2. So down here we get 210, here we get 330. We convert it to radians and we have 7 pi over 6 and 11 pi over 6. This is where it would be helpful to be looking at your unit circle if you need it. So let's go look at the unit circle. So in the first quadrant, you can see 30 has a sine of 1/2. Remember, the second part of the ordered pair is your sine. So we know it's a 30-degree reference. And down here, it's 210. And over here, it is 330. And you can see that -1/2 there and -1/2 there. All right. So those would be your two answers. Solving a linear trig equation. So it's kind of what we just did. 2 sine theta plus square root of 3 equals 0. We have the same kind of parameters. We're going to subtract the square root of 3 over here, and we're going to divide by 2. In that interval, there's two angles for which sine is equal to negative square root of 3 over 2. If we go back to our unit circle, and so sine is square root of 3 over 2 in the first quadrant there at 60, but we need it to be negative. So down here, it's 240. That's 4 pi over 3. And over here, it's 300, and that's 5 pi over 3. So you can use your unit circle to help you with that, or you can begin to be learning those. But that is one way, if I can get back to my thing. Okay, now let's look at this one. Tan of theta minus pi over 2 equals 1. So the period for tan is pi. So in that interval, the tan has the value 1 when the argument is pi over 4. But let's look at what happened to get to that. So we have theta. So what that was going to give us, we know that tan of this is equal to 1. And if we look at our unit circle, let's just go back here. So tangent of 45 is 1, because tan is sine over cosine. And so that square root of 2 over 2 over square root of 2 over 2, that's equal to 1. So every angle that's referenced to 45 is going to fit that bill. So if we go back here, this keeps moving when I go back. All right, so this argument says that angle that we should get there that gives us 1 is 45. So we take that argument and set it equal to pi over 4 plus, and we could rotate around and get k times pi, because that is our period, was pi. So if I add pi over 2 over here to the pi over 4, I get 3 pi over 4 plus k pi. In that interval, there are two solutions, 3 pi over 4 and 7 pi over 4. Let's look at our unit circle one more time. 3 pi over 4 is over here because we're positive. We're also positive down here at 5 pi over 4. Those both have a tan of 1. Okay, we had 7 pi over 4. Let's see. I wasn't even looking at that. So we're here at 3 pi over 4, and yes, it's positive here, but we had to add pi k. So we had to add a whole 180 degrees, and that gets us over here to 315. If you see, that's a straight line. So we get over here because we added pi, and we have 7 pi over 4. So that's where we got that one. Let's go back. All right, solving it using the calculator. So it's another way to solve. To solve tan theta equals -2 on a calculator, be sure you're in radian mode and then use the tan inverse case. So you would do tan inverse of -2, and you get this. And you would round to 2 places. And you'll get -1.11 radians. So that is one solution, but we have our interval from 0 to 2 pi. And so we need to, since the period is pi, then we have to do pi minus 1.11 and 2 pi minus 1.11. Those are solutions that also there. So in our picture here that we can see, let's make that a little bit bigger. All right, so in our picture, here is the -1.11. That is the original solution. Then we also have pi minus that. That's going to give us right here. And then we have 2 pi minus the 1.11. So if you do those on the calculator, you get 2.03 and 5.17. So you have those solutions. In quadratic form, this is another one. So we have 2 sine squared theta minus 3 sine theta plus 1 equals 0 in this interval. So it looks like it's quadratic. So if you let sine theta be x, you could rewrite it. So over here is x equals sine theta. So you have now 2x squared minus 3x plus 1 equals 0. That looks more familiar. We factor that and we get those two factors. Then take each of those, set them equal to 0, and put your sine theta back in for x. So here we have 2 sine theta minus 1 equals 0. So sine theta equals 1/2 if you add the 1 and divide by 2. Or sine theta equals 1. If you solve each of those in the interval, where is sine theta equal to 1/2? And we can go to the unit circle and get that. We would get pi over 6 and 5 pi over 6. That's where it's positive. And then where is sine theta equal to 1? That's at pi over 2. So if we go back to our unit circle just to see that, so sine theta is equal to 1/2 at pi over 6, and it's also equal to 1/2 here at 5 pi over 6. And then at pi over 2, sine is 1. So you can totally use that to do that. So that's quadratic in form. Then we haven't really talked as much about our identities in solving these, but we can use identities sometimes to help us solve. So this one says 3 cosine theta plus 3 equals 2 sine squared theta. And so we have now a sine and a cosine, and that's a little different. But since we have cosine theta here, we can change this sine squared because the identity, the original identity that we know says sine squared theta plus cosine squared theta equals 1. So if we subtract the cosine squared theta, we now can write sine squared in terms of cosine squared. So that's the substitution right there. You distribute, and you have 2 minus 2 cosine squared theta. Now let's get the cosine squareds together. So let's get everything on one side is what we need to do. So we're going to add 2 cosine squared theta here. We've got this 3 cosine theta. We're going to subtract 2, so now we have 1, and we have it equal to 0. We can factor that, and we get these. We solve, we get cosine theta is -1/2 or cosine theta is -1. Using your unit circle and solving for those, you get the 2 answers for the cosine theta equals -1/2, and then cosine theta is -1 at pi. So you have 3 solutions for that. There is another couple, there's another one using identities. So in this one, we have cosine squared theta plus sine theta equals 2. So we've got sine and cosine again. We want to think back to that Pythagorean one. We're going to substitute for cosine squared and make it 1 minus sine squared. And so when we, if we multiply, if we just take the parentheses off and we multiply through, let's see, we've got sine squared minus sine theta and plus 1 equals 0. And that happened because we subtracted the 2, and then we had a -1. So we would have a -1 there. Let's see what's happening there. So right here, if we remove the parentheses and we multiply the entire equation by -1, we have -1 plus sine squared minus sine theta equals -2. And so this was a -1. Then I'm going to add 2 over, and so I end up with a +1. So this is my equation. If you tried to factor, you're not going to be able to. And the suggestion here is to look at the discriminant. And the discriminant equals -3, which tells you there's imaginary solutions. So the solution set here would be the empty set. Solving using a graphing utility. So in this one, they went to the calculator and they put the left side in y1. And so that's looking like that. And then they put 3, y2 is equal to 3. And they found, where do those two intersect? So 1, 2, 3 spots. And you can find that with second calc 5, which is intersect. And you get these 3 solutions. So that's a pretty easy way to do that. The last example from the book is one using a double angle, and I'm going to save that one because we have one in our problem set that is a little bit easier, and we'll go through that one. But that one is there for you to look at. Let's go look at our problem sets. Let's go back to the top. So find the exact values of the following expressions. So this is where you could just easily use your unit circle. The sine of pi over 6, the cosine of 15 pi over 4. So sine of pi over 6, if we went over here, pi over 6 is right here, the sine is 1/2. Now 15 pi over 4, where is 15 pi over 4? Well, if we go back, so cosine of 15 pi over 4, let's think about that. If we divide 4 into 15, we get 3 3/4. So let's go back to the unit circle and just see it. So right here, if we're starting at 0 and we go 1 pi, 2 pi, 3 pi, and if we went all the way, there'd be 4 pi, but 3/4 pi is right here. And so that's 3/4. So 315 is our angle, and square root of 2 over 2 is what we are looking for. So that's cosine, square root of 2 over 2. All right, so that's using your unit circle to do that one. Find the solutions in this one. We have 3x squared. This is just a regular quadratic just to get you to practice factoring. And we end up with x is -1/3 and x is 7. That's really not trig, it's just helping you get ready. All right, we're also getting ready here by solving this with our calculator. So we have 7x cubed minus 8 minus x plus x squared. Where did that all come from? I moved all of this to the other side. And you don't have to order or anything. You just put it in like that. You put y2 to be 0. So when you graph it, you get this, and you find the intersection is this. 1.04, it said to round to 2 places. All right, now this is our first trig one. So we have 2 sine theta plus 4 equals 5. Subtract the 4, you get 2 sine theta is 1. Divide by 2, you got sine theta is 1/2. Where is sine theta 1/2? Well, it's in the first quadrant and the second quadrant. If we go here, where is it equal to 1/2? Right there at pi over 6, and right here at 5 pi over 6. We knew that sine was positive, these two quadrants. That all has to be in your head. Okay. All right, we're back here. All right, 4 sine theta minus 2 equals 0. Add 2, divide by 4. Where is sine theta equal to 2 over 4 or 1/2? We get the very same answers we had in the question 4. 4 cosine theta plus 4 equals 0. Subtract 4. Now divide by 4 and you get cosine theta is -1. That is happening at pi. 7 cotan theta minus square root of 3 equals 0. So add square root of 3 and you have cotan theta equals square root of 3. Where is that happening? So let's go back to our unit circle and look at something. First of all, they do give you some tan functions here. Tan is sine over cosine, but cotan is cosine over sine. And so if we look here, cotan is cosine over sine. So that would be square root of 3 over 2 over 1/2. When you flip the 1/2 and you multiply, those 2's are going to cancel out and you get square root of 3. That makes sense. If you flipped this one and you fixed it, you would get square root of 3. So we're here at pi over 6, and cotan is also positive down here. So we'd have one at 7 pi over 6. We'd get the same thing. So use your unit circle. All right, number 8. 4 secant theta plus 6 equals -2. Subtract your 6, you get -8 there. Divide by 4, you get secant theta is equal to -2. Well, secant is 1 over cosine, so let's go back and look at our unit circle. So just remember when we go look at it, secant is 1 over cosine. So we are looking for where is cosine equal to -1 over 2. So let's go here. So cosine is our first part of the ordered pair, and look here, -1/2. So that would mean that secant would also have that. So that would be 2 pi over 3. And then also here in the third quadrant, we would have negative. So at 4 pi over 3. So we were looking for a cosine of -1/2, and we found it in those two. So our solutions are 2 pi over 3 and 4 pi over 3. All right, let's do 9. 16 cosine squared theta equals 4. So we're going to divide the 16, and we get cosine squared theta equals 4 over 16, or 1/4. Now here we have to be careful. We're going to take the square root of both sides. So cosine theta equals plus or minus the square root of 1/4. And that's a perfect square, so we get theta is equal to plus 1/2. Where is cosine theta equal to either plus or minus 1/2? We have 1 in every quadrant. If we go to our unit circle, and we can see that pi over 3, we have a 1/2. And then we have here we have a positive 1/2. And we're looking for either negative or positive. So we've got pi over 3 here. We've got 2 pi over 3 here. We've got 4 pi over 3 here and 5 pi over 3 here. So we were looking for negative 1/2 and 1/2. We had one in each quadrant. So when you have something where you end up like that, where it was squared, you're going to have 4 solutions. All right, number 10, tan squared. So we're going to end up with the same idea here. So 4 tan squared theta equals 4. Divide by 4, you've got tan squared theta is 1. Where is tan theta equal to plus or minus 1? And we know that's a 45-degree angle that gives you a tan of 1. So we're going to look for 1 in every quadrant. And you get pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Number 11, similar. We had 4 sine squared minus 1 equals 0. You're going to add that 1 and divide by the 4. So you end up with sine theta is equal to plus or minus 1/2. So we're looking for sine theta. Where's it going to be either positive or negative 1/2? And we have one in every quadrant. Pi over 6, 5 pi over 6, 7, and 11 pi over 6. All right. We've got just a couple more. And these are using those multiple angle identities. So let's look here. See how this one, how we should attack this one. Cosine of 3 theta equals negative 1. In the interval, cosine theta is equal to negative 1 at pi. And so we're gonna do something with that over here. But let's do this. Let's take that argument and set it equal to pi plus 2k pi. We know that cosine's equal to negative 1 at pi. If we go look, negative 1 right there, that's at pi. All right. So we're going to set it there, and we know that if we went around a full revolution, we'd be back there. So we'll say plus 2k pi. Now you'll divide by the 3, and you get theta is equal to pi over 3 plus 2k pi over 3. All right, so we know there'll be several angles within that revolution that we can use, and we'll just try. We'll start with 0, 1, 2, and 3. And we're going to fill into this. If I let k be 0, then this thing is gone, and I just have theta is pi over 3. That's one solution. If I let k be 1, then this k became 1, so now I have 2 pi over 3 plus pi over 3. So that's 1/3 plus 2/3, that's a whole pi. If I let k be 2, 2 is here, so that's 4/3 plus 1/3, that's 5/3. And I can't go any more because then I would be out of my interval because I'm at 5/3 pi. And if I go more, I'm going to be out of the 2 pi. So these would be my solutions. So you would do the same thing here. Sine 2 theta is 1/2. And in the interval, sine theta is 1/2 at pi over 6 and at 5 pi over 6. So we have to do that setting the argument equal to both of those. So 2 theta is equal to pi over 6 plus our 2k pi. It's also equal to 5 pi over 6 plus 2k pi. So we divide by 2 on both of those, and we have these. All right? I let k equal 0 for 0 and 1. I think that's all we're going to get to on that one. And we get pi over 12, or we get pi over 6 plus 2 pi, and that's going to give us, if we're 1, yes. So we're here. So pi over 12 plus 1 pi. That would give me 13 pi over 12. Over here, if k is 0, I get 5 pi over 12 because I divided by the 2 here. So if k is 0. If k is 1, I've got 5/12 plus 1 pi, so that'd be 12/12. That'd be 17 pi over 12. So you have 4 answers. That's how you would have to do that one. I think that should get you through 7.3.